go over section 3.1, which we will learn about higher order derivatives, velocity, and acceleration. So previously, we learned how to take the derivatives and we learned their applications. Another application of derivatives is seen in the study of motion. So if you have any background in physics, you know that the velocity of a car is the rate of change of displacement at a specific point in time. And this definition, I know because it says rate of change, corresponds to the definition of a derivative which shows us the rate of change. So in order to apply derivatives into the study of motion, we need to learn also higher order derivatives. We know that if we have a function, let's say in this case 10x to the power of 4, I know that I can take its derivative and represent it by the prime symbol on top of the function right here. However, if I want to take the derivative of this derivative, I can also do that by doubling the prime superscript, like over here, and calling it the second derivative. In Leibniz notation, that is represented by d2y over dx squared. And if you want to know where this comes from, it is by taking the derivative of a derivative, which gives it its superscript of 2. And we will learn in a bit why we need higher order derivatives in order to solve velocity acceleration problems in the study of motion. But before that, let's solve a problem with higher order derivatives to get familiar with it. So in this problem, all we need to do is determine the second derivative of fx equals x over 1 plus x when x equals 1. So like I said, the first thing I'm going to do is take the derivative of this, and then I take the derivative again for the second derivative. So let's start by taking the derivative of this. Because I know quotient rule is just going to be a little longer, I'm going to rewrite fx as x and 1 plus x to the power of -1 just to make it easier. So now I can use the product rule instead of the quotient rule. So me using product rule, remember how product rule goes. I'm going to rewrite it here just in case. So product rule states that first, if you have like hx, you take the derivative of fx first, keep gx the same, and then we do plus fx and then derivative of gx. So in this case, my fx is here, and my gx is this. Now I can apply the product rule, which I'll start by taking the derivative of fx. When you take the derivative of x, which you can apply the power rule, but whenever you have only x, it just means 1, because x to the power of 1, apply the power rule, you will end up with x to the power of 0, which will give you 1 anyways. I keep gx the same, so 1 plus x to the power of -1, plus, keep fx the same, so I have x over here. Now apply the derivative for the second gx function. So I'll start by the power rule. I know that I start from the outside, bring this -1 to the front by power rule, keep inside the same because this is not only x, I see that this is a function. So remember, whenever we had a function, we keep inside the same and we do -1 to the power again, so -2 by the power rule. But now I need to multiply it by the derivative of the inside. I realize when I take the derivative of 1, it's a constant, so that would be 0. And I look at x, and like I just said, it will just become 1. So I only multiply it by 1. So now I have the derivative saying 1 over 1 plus x minus, because I have a minus right over here, x over 1 plus x to the power of 2. Now to put these together, I'm going to multiply this one by 1 plus x, so the denominators are the same. When I do that, I'm going to end up with 1 plus x all over 1 plus x squared minus x all over 1 plus x squared. So now I can cancel the x's out. So because this is a plus x, and when you multiply these, you're going to get negative x. So my answer for the first derivative is 1 over 1 plus x squared. Now that I have my first derivative, I can take the second derivative now by taking the derivative of whatever I ended up with, which is here. So I can rewrite this instead of applying quotient rule, which is going to be again long. I'm going to rewrite this as 1 plus x to the power of negative 2, which represents the same thing. So from here, I will apply my power rule. But remember, again, this is a function, which we learned before. Whenever you have a function inside, instead of just x, you apply the power rule from the outside and then times it by the derivative of the inside. So when I do that, I'm going to represent it by double prime x, and that will equal to me bringing my n value, which is a power value, to the front. So I have negative 2, and I'll keep inside the same, which is 1 plus x, and I do minus 1 to my power to end up with negative 3. Now I take the derivative of the inside, which we did before. Constant will give me 0. Taking the derivative of x will give me 1, so it's just multiplying by 1. So I ended up with negative 2, 1 plus x to the power of negative 3, which I can rewrite, if needed, as negative 2 over 1 plus x cubed. So I found my second derivative. All I need to do is, they're asking for a specific point, which I can plug it back in. So they're asking for the second derivative, which I found, but they say like at this specific point, which is x equals 1. So when I do that, all I'm going to do is plug in 1. So I can rewrite it as sf double prime, and then my x is 1. And I'm going to plug that in. So I have negative 2, 1 plus 1 cube. That will give me negative 2 over 2 cube. And that will give me negative 2 over 8, which I can simplify it into negative 1 over 4. And that's my final answer. So now back into why we need higher order derivatives for the study of motion. We need it, it's because we need to calculate the rates of change. When we study a motion, often we will encounter position time graphs such as this, which is commonly denoted as ST. Examples can be car moving along a straight section of road, a ball being dropped from the top of the building, etc., etc. So now if we have the position of the object as a function, I can find also its velocity by taking its derivative. Because rate of change in position with respect to time will give me its velocity, therefore how fast it is going. Now, if I take the second derivative, so derivative of velocity, I will get acceleration. Because rate of change in velocity represents acceleration, showing how fast the object is accelerating, so changing its velocity, the units for each of these usually can change depending on the question. So for position, it's going to be meters. And for velocity, it's going to be meter per second. Sorry for second derivative just blocking the way. But just to show that if you want to go straight from position to acceleration, you take the second derivative. Other than that, in order to go to position to velocity, you take derivative. Velocity to acceleration, you take derivative. And the units for acceleration is meter per second squared. So this here is straight from your Nelson textbook and summarizing how to find the velocity, which I told you guys beforehand. It summarizes how to go from acceleration to velocity to position, as well as showing the second derivative being acceleration. The only thing to note from here is velocity and speed are two different things. You can think of velocity as speed with direction, where speed doesn't have a direction. So for example, for velocity, if the object is moving to the right at time t, vt is positive. If the object is moving to the left, velocity is considered to be negative. Same thing for upwards and downwards. Upwards is considered positive while downwards is considered negative. So if velocity equals to 0, so let's say it's not positive or negative, that means that the object is stationary at that time. So due to the direction of the velocity, if a problem asks you to calculate the speed, you take the absolute value of velocity, which is shown right over here, because direction doesn't matter for speed. Also for acceleration, an object is considered accelerating if both the velocity and acceleration have the same sign, meaning either they're both positive or they're both negative, so they're going in the same direction. However, if these signs are different so that the velocity is negative and acceleration is positive, vice versa, the object is decelerating or slowing down. So a problem to get started with, an object is moving along a straight line. Its position, which is represented by st to the right of a fixed point, is given by the graph shown right over there. When is the object moving to the right and when is it moving to the left? And it's asking when is it at rest. So remember previously what I told you guys is the velocity is going to be positive if the object is moving to the right. So if I know that wherever on this graph the velocity is positive is when that the object is moving to the right. And remember how you find the velocity. Right now I have the position graph, not the velocity. But if I take the derivative of this, I will get the velocity. I don't have a function to take the derivative directly, but I know that derivative represents a slope of a tangent. And right now over here, st increasing, like right over here, if I get a point right here, my tangent is going to be positive. So wherever the position is increasing, that's when the object is moving to the right. So let's say if I had a point right over here, my tangent would be something like this, which would give me negative. So that means at that point it's moving to the left actually. So I need to find wherever it's increasing. So I know that the position is increasing until t equals 2, so from t0 to t2. As well as right after 6. So right after 6, I also see that it's increasing. So I can say when my t is bigger than 6. So like I said before, right over here, if I got a tangent, it would be decreasing, and I said that would be moving to the left. So I know the function starts to decrease from the point 2, and it goes down until the point 6. So I'm gonna say it's moving left from 2 to 6, so those are my intervals. But realize that I don't put these as equal sign. So I don't say it's moving to the right including 6. And that is because I have a section where I say where the object is stationary or at rest. So when I look at the graph, I realize at t equals 2, which is right up here, my object is changing its position from going to the right to left. And over here, if you put a tangent, it will actually be horizontal, which will tell you that the derivative is actually 0. So that means my velocity is 0. So one of my points I can directly say when t equals 2, my object is at rest. Same thing for t equals 6, which is right over here. Oops, which is right over here. Again, if you put a tangent, it's going to be horizontal, which means my velocity is 0 at that point, so also t equals 6. Another thing you might put is maybe 0, but only 2 and 6 is enough. So that would be my answers in terms of where the object is moving. So for this question, it's saying the position of an object moving on a line is given by the function over there, where t is bigger than 0 or equals to 0, where s is in meters and t is in seconds. The first part is determine the velocity and acceleration of the object at t equals 2. So already, because I know st represents the position here, I know when I find the velocity, I take the derivative, and to find acceleration, I take the second derivative. When taking the derivative, I'm applying the power rule over here. So I keep the constant the same, which is 6 over there. Bring 2 to the front, keep t, and do minus 1 to the power, which will give me 1. Minus, bring over here, bring 3 to the front, keep t, and do minus 1 to the power, which will give me 2. So as an answer, I have 12t minus 3t squared. So now that I have my derivative, it wants it at t equals 2, so I will plug that in. So my derivative at 2 will give me the value of 12, 2 minus 3, 2 squared. So here will give me 24, where here will give me 2 squared will give me 4, 4 times 3 will give me 12, which will end up with the value of 12. So my values for velocity is actually 12 meters per second. So now in order to find acceleration, I'm going to take the derivative of that derivative again. So here I realize if I take the derivative, I will end up with 12, keep the constant. And if you apply the power rule again to t to the power of 1, which will give you 1. And here I will keep my constant in the front, so minus 3. Bring that 2 to the front, so I will have 2t. And when you do minus 1, it will give you 1. So you will end up with 12 minus 6t. Now all I need to do again, plugging the value of 2 to my second derivative, which will give me 12 minus 6 to times 2, and I know that will give me 0, so my acceleration is actually 0. The second part is saying at what time or what times is the object at rest. So the object will be at rest whenever the velocity is 0. So remember from the graph from the previous problem that we solved, we said the object was at rest whenever my tangent was horizontal, right? And that happened like t equals 2 and t equals 6. Same thing over here. So whenever my velocity is 0 is where my object is at rest. So I will start by equaling my function, my velocity function to 0. So I realized from this function I can actually take out 3t, which I will end up with this, where I can separate these into 2 and equal it to 0. So the first part will be 3t equaling to 0, which will give me a value of t equaling to 0 when you divide each side by 3. 4 minus t will equal to 0, where I can get that 4 as a negative to the other side. So that would give me negative t equaling to negative 4, which if I divide each sides by negative, that will give me t equaling to 4. So I found my values for when my object is at rest. So the third part is asking in which direction is the object moving at the time 5 seconds. So because it's asking which direction is it going, so like right, left, we saw that we did that by using velocity. So if my velocity is positive, it's moving to the right. If my velocity is negative, it's moving to the left. So I can use my velocity function again. So I see that when I plug in 5 for my function, I get the value of negative 15, which gives me the conclusion that the object is moving in the negative direction. So in order to learn when is the object moving in a positive direction, we know that we use the velocity function again, and I know it goes to the positive direction when my velocity is positive. Here I can just write my function being bigger than 0 to represent the positive, and then I can divide each side by 3. So in order to eliminate from here the negative t, I'm going to divide each side by negative, which will give me t squared minus 4t now. And I change up the sign because whenever I divide by a negative, the sign flips. So now I took the t out to get t, and then in brackets t minus 4 being less than 0. So from here, I can have two cases. So I consider that, let's say, like the first factor is positive and the second factor is negative, vice versa. So we're trying to figure out making one of them is positive while the other one is negative. So if I count t minus 4 less than 0, that will give me, if I send the 4 to the other side, t being less than 4, that means I need to count the other t, which is right over here, positive. So this gives me these two, and my case will be the opposite, where instead of saying t minus 4 less than 0, I'm going to make it positive. So that will give me t being bigger than 4, and I'm going to count t being less than 0. However, I realized that when t is less than 0 and it's bigger than 4, it doesn't really give me a solution, so I don't consider this case 2, therefore I use my case 1. So I say that my velocity is positive when it's between 0 to 4. The last point is asking, when does the object return to its initial position? Since the initial position over here can be represented by st being equal to 0, because st is in meters, so 0 meters would be my initial position. It doesn't ask for initial time or whatsoever, it's asking for the initial position. And I know it starts from 0 meters and it's probably going to end up at 0 meters at some point because it says returning, right? So it's not t equals 0, but I will find another time. But what I can do is I already have the function for the position, which I can equal it to 0. So if I do that, I'm going to get 6t squared minus t cubed equaling to 0. Now I can take out t squared out of the function. Now from here I can separate it into 2, saying my t squared equals to 0. When you take the root for each side to leave the t alone, I will get t equaling to 0, which I expected. So when t equals 0 seconds, it's at 0 meters. The other one is 6 minus t equaling to 0, which when I send 6 to the other side as negative, I will get negative t equaling to negative 6. Divide each side by negative, so I will get t equaling to 6 seconds. So I can say my object returns to its initial position at t equals 6 seconds. So a baseball is hit vertically upward. The position function st in meters of the ball above the ground is given by the function where t is in seconds. The first portion is saying determine the maximum height reached by the ball. So don't let it confuse you because it doesn't say velocity or acceleration. What it means by maximum height is, let's draw the situation, what's happening, right? So there's a man right over here. Sorry for my Batman. And he's throwing a ball upwards. What's going to happen to this ball is it's going to go upwards, upwards, upwards. And at this point, it's going to slow down as it goes upwards, as it reaches its maximum height. And then due to gravity, it will come back down, right? It will come back down and accelerate again. So at this portion, it accelerates, slows down, slows down, slows down, slows down. And here is when the velocity is 0. That's the point we need. At maximum height, the velocity of the ball is 0. So if you think of, like, if you throw a ball in real life, you would see, if you observe it, when you throw it, at the top point, it looks like it stops for a second and then like comes down, accelerating. So again, it slows down and starts to accelerate as it goes down due to gravity. So since I know now at maximum height my velocity is 0 and I have the position right over here, I can find my velocity function and equal it to 0, so I can determine when that I reach my maximum height, or not even when, what is my maximum height. So taking a derivative of st, I'll start with this portion right over here, which we do keep the constant, again, whatever is there. So I have t squared, which I apply power rule to. I'll bring 2 down and do minus 1 to the power, so I will end up with getting 2t. Now I move on to here, which I will keep the constant 30, and if you apply power rule to t to the power of 1, it will give you 1. And I know for the constant, if you take the derivative, it will equal it to 0. So my velocity function will equal to negative 10t plus 30. So now that I have my velocity function, all I need to do is equal this to 0 so that I can find the time at when I reach my maximum height. So from here, it's easy. I will send the 30 as a negative to the other side. So I have negative 10t equaling to negative 30. Divide each side by negative 10, you will end up getting 3. So at 3 seconds, I reach my maximum height. But it doesn't ask you when, it says determine the maximum height. So in meters, what's my maximum height? All I need to do, since I know the time, is plug that back into my position to find in meters where is my maximum height. So if I do that, I will end up getting S3 equaling to -5, 3 squared, plus 30, and multiplied by 3, and plus 1. So as an answer, I would get 46 meters. So I reach my maximum height where it's 46 meters. The second point is determine the velocity of the ball when it is caught 1 meter above the ground. So if you think about it again, let's say this person again threw it and the ball starts to go upwards, blah, 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 and it comes down. That's my position graph, right? So it's just a half circle. And let's say this point is my 1 meters. I see that it either is over here, and I see that the ball is at 1 meter above the ground at 2 points. So I'm going to have 2 time values. In order to find that, I can use my position to equal that position function to 1 meters to see at what times my ball is 1 meter above the ground. So that will be 1 equaling to -5t squared plus 30t and plus 1. Send that 1 to the other side, I will get 0 equaling to -5t squared plus 30t. Now I can take out 5t out. So instead I took out -5t. And from here I can equal these two to 0 separately, which I'm going to end up with -5t equaling to 0, divide each side by -5, so I got t equal to 0. So that's reasonable, because if I think of it, if a person is throwing it, maybe like a person is throwing it from 1 meters, right? And the second portion is t minus 6 equaling to 0, and send that 6 to the other side, t equals 6 seconds. So I also know that this point I was talking about is at t equals 6 seconds. So now all I need to do is plug in that 6 back into my velocity function. So I don't put t equals 0 just because it is the time where he throws it, but it's asking for when it is caught, right? So if, let's say, there's another person right over here who's catching it, or it's the same person, doesn't matter. But because it says caught, I'm going to use the other point. So all I need to do is plug in 6 for my t value, which will give me -10, 6 plus 30, which I will end up with -60 plus 30, and that will give me -30 meter per second. The negative value makes sense. It's because it's moving in a negative direction. It's going down. So that's why it's negative. So my answer would be -30 meter per second is when the ball is caught 1 meter above the ground. If you have any questions or problems, make sure you go to our forum section at our website where we can answer all of your problems regarding to either this video or other courses as well.